Okay, good. I hope my screen is visible, right? All right, good. So, welcome to a new topic that is uh, linear regression. And under linear regression, I know some of you know when we talk about linear regression, we are talking of predictive analysis. Okay, why? Because under linear regression, we usually build some linear models that help us in what? In prediction. Okay, so linear, when we talk about linear regression, we are talking more of predictive what? Predictive analysis. Predictive analysis. So, what is linear regression? Or what do you understand by the term linear regression? So, for linear regression analysis, it is used to predict the value of a variable based on the value of another variable. Like, for example, using the example of the umbrella cells, okay, we are using the amount of rainfall, okay, we are using the amount of rainfall to predict what? The umbrella cells. Okay. We are using amount of rainfall to predict what? To predict the umbrella cells. Meaning now, okay, that is umbrella cells will be our output. Okay. Then we'll have a constant. Let's call it A. As I said, now this constant is the slope. Okay, or the gradient. Then we have rainfall amount. Let's say R, it's what? R, it's a variable. Okay, yes, it is our independent variable. So this is rainfall amount in millimeters. Okay, then plus another constant, call it maybe B. And this constant, it's we usually call it the y-intercept. So for linear regression, we are talking of what? Two variables. Okay, the variable which we are predicting and the variable which we are using to predict. So this will be our output, okay, in the model, and this will be our input in the model. Okay, right. So the variable you want to predict is called dependent variable. So here, u, okay, this is the model. Okay, so u will be our dependent variable. Okay, this will be the dependent variable. Then our that is our r. Okay, r, this is the amount of rainfall, will be the independent variable. So whatever we are predicting, it's what? It's independent. It's dependent. Sorry, it is dependent variable. And whatever we are using to predict, it is what? It is the independent. Okay. So that's why we are saying that the variable you want to predict is called the dependent variable. The variable you are using to predict the other variable value, it's called what? It's called independent variable. So this form of analysis estimates coefficients of a linear equation. Remember, we have these coefficients. The coefficients are our constants. Okay, so we have coefficient of rainfall amount, and then we have the other coefficient, which is the y-intercept. Okay, so we are saying this form of analysis estimates the coefficients of the linear equation involving one or more independent variables that best predict the value of the what? Of the dependent variable. Linear regression fits a straight line, okay, or surface that minimizes discrepancies between predicted variable and actual output number. Okay, so take note of this statement that linear regression tries to give us that is a line of best fit, okay, that minimizes the error term, or that minimizes the standard error here. So when we talk about error term, we are talking of that is we are talking of the vertical deviations. Okay, maybe let me illustrate that. Okay, so let's assume we have this kind of graph. We have our data points here. Let me just do that is a line of best fit. So we have that is some points, data points, which are what? Which are within the line. And also we have some other data points which are outside the what? That is the data that is the straight line. Okay, so the distance between these data points to the line of best fit, okay, that variation, okay, it's what we call what? It's what we call the error term. Okay, the error term is it's like that is the distance between what? Between that is the values to the what? To the line of best fits. That's why you can say we are talking of vertical deviation. Error terms, they are vertical deviation, okay, to the point of the that is of the straight line. So regression, we are saying that the linear regression fits a straight line or surface that minimizes the discrepancies between the what? The predicted and the actual what? And the actual values. Okay. So there are simple linear regression calculators that use least square methods to discover the best fit line of the what? Of a set of paired data. Okay, and you can estimate the value of x, that is dependent variable, given what? Given the independent variable. We shall do an example of that. Okay, yes, let's continue with the notes. So, like for example, let's assume now we have this example of that is the salary. So this is the salary amount, okay, and this is experience in years. Let's assume that, okay. So you can see we are assuming that, okay, the higher the that is the higher the or the higher the experience you have, okay, of course you are getting what? You are getting more pay. You can see the difference between what this person with 10 years of experience is earning, okay, and the person with what? With 5 years of experience, what is earning. Okay, you can see for the person with 10 is earning between 100,000 and almost 150 between that. Okay, and then for the person with years of experience is earning between 50,000 and what? 100,000. So linear regression performs the task to predict an independent variable. Let's assume V, that is Y. Based on a given independent variable, let's assume it is what? X. So this regression technique finds out a linear relationship between what? Between X, which is the input, and Y, which is the output. Hence the name linear regression. Why? Because they are trying to that is to identify or to find a linear relationship between what? Between these two variables. Like in the figure below, or in this graph, okay, X is the input and it's in work experience, that is in years. Then Y is the salary of a person. Okay, so the regression line is the best fit line for what? For a model. Okay, so you can see this is the regression line. This is the regression line. Okay, good. Of course, we usually have somewhat. We usually have some assumptions when it comes to linear regression. And the assumption which we usually assume, I'm just giving you that is a brief on the assumptions as we will discuss them here in depth. Okay? Yes. So we have major assumptions, that is linearity assumption, meaning there must exist a linear relationship between what? Between X and Y. That's why we are saying that the relationship between X and Y should be what? Should be linear. Then we have homoscedasticity. Okay. Then for homoscedasticity, we are saying that the variance of the residuals is the same for any value of what? Of X. Meaning we are almost having the same distribution of what? Of our error term. Okay. Residual, it's also known as the error term. Residual is also known as the error term, okay? Also known as the vertical deviation. It's also known as the vertical deviation. Then we have independence, okay? That is, the observations are independent of each other, okay? Meaning it's like under binomial distribution assumption. That is, we have independency, like outcome of one trial cannot influence the outcome of the second trial. Okay, but we'll discuss more that. So independency meaning they know that is uh, each value is mutually exclusive to each other. Okay, yes. Then we have normality. For normality, we are saying that for any fixed value of X, Y is normally distributed. Okay, so we are assuming that is our output is normally distributed at a point, or assumes a normal distribution. Any question up to that point? Any question up to that point? All good? Thumbs up. Any? Yes, Kennedy, Dennis. All right. Yes, Naomi?
Sorry, that was by mistake.
Okay. All right. Okay, so let's continue. Now I want us to explain this. You can see this is a equation of a straight line, or it's a basic model. Okay, why? Because we can assume this is umbrella cells. Okay, we can say this is the y-intercept, and this is what? This is our the slope. Okay, and then this is our rainfall amount. Okay, it doesn't matter the arrangement. Okay, yes, but this remains that is a linear equation. Okay, good. Now let's assume maybe we are doing that is we are keeping this in machine learning. Okay, remember we have our input, so this is our data, our input data. Okay, meaning this data we can now maybe divide it into two, that is training data and testing data. Okay, like for example, we are trying to do a classification, what an example maybe of a classification example of that is supervised machine learning. Okay, so let's say you have like 1,000, okay, 1,000 pictures of cats and dogs. Okay, so you can now divide those pictures, like you have 800 to be pictures of the cats and dogs, meaning it will be like 400 400. Okay, and then you also get now the remaining 200, that is 200. You now get like that is 100 for cats, 100 pictures for dogs. Okay, so you can see now our data split is like 80% to 20%. Okay, now when it comes to machine learning or training, we usually now use the 800 what, or the 8%. Okay, depending with your split. Let's say assume 80% of what, of the pictures to train your model. Okay, and then you now use what, you now use the 20% of your data or images to test the model. Okay, so let's maybe go through, that is the hypothesis function for linear regression. Okay, so while training the model, we are given what? The X input, whereby now the X input is the what? Is the training data. And in this training data, I've said we can divide it into two. That is training and what? Testing data. Okay, it can be training and testing data, meaning this will get the larger portion of what, of your data, let's say 80%, and this will take that is 20% portion of your data. But that is when it comes to what, machine learning. So in this topic I don't want to discuss much. Okay, I don't want to discuss much on that topic of splitting the data. Okay, otherwise let's now continue with what, with our that is with our major topic. Good. So we have X, it's our input data. For now, know that. Okay. Then we have Y, it's our output data. Okay. All the labels. Let's say it is our output data. Also for that, know up to that point. The next topic about maybe machine learning, it will be discussed by machine learning, that is tutor. Okay, so when training the model, it fits the best line to predict what, to predict the value of y for a given value of what, of x. The model gets the best regression fit line by finding the what, the best coefficients. Okay, and this will now bring us to the following, that is to the next topic. How can we optimize, how can we optimize our what, that is our constants. Okay, so for this we are going to use different optimization methods, okay, to be discussed on the next slides. Okay, so you can see theta 1, okay, indicates what, the y-intercept. Okay, this indicates the intercept or the y-intercept. Then theta 2 indicates what, coefficient of our independent variable, coefficient of our independent variable. All right, okay, that's good. Now let's go to types of what, linear regression. So for linear regression, we have, of course, here they are talking about two, but we have almost five. Okay, we all have almost that is five types of regression. Okay, so we have, but now these are types of what, linear regression, meaning we are discussing about a linear relationship like a straight line. Okay, But when it comes to types of regressions, okay, we have types of regression. We have almost 5 types of regression. That is simple linear regression, multiple linear regression, logistic regression, discriminant regression. We have multinomial something regression. We have almost 5. Okay, and I can only remember uh, that is 4. Okay, yeah, you can go and maybe check more types of that is types of regression. But for linear regression, we only have 2 major types of linear regression. Okay, and that is simple linear regression, meaning for simple linear regression it has only one independent variable. Like for example, it will be y equal to mx, okay, plus what? Plus c. You can see we only have one independent variable. Okay, but now for that is for a multiple linear regression, okay, we have more than what? We have more than one independent variables. Okay, so it will be like that is y is equals to mx maybe 1 plus bx2, okay, plus c, okay, and maybe you can also add the what? The error term, that is epsilon. Epsilon is the error term or our vertical deviation. Okay, right. So we have our first constant, our second constant. Okay, and also that constant. Okay, but now for independent variables, you can see also we are having what? We are having more than one independent variables. Okay, so for this reason, we are having what? We are having or we are talking of multiple linear what? Multiple linear regression. Okay, like for example, if a single independent variable is used to predict the value of the numerical dependent variable, then such a linear regression algorithm is termed as simple linear regression. Why? We are only having a single independent variable. What about multiple regression? So let's assume if we have more than one independent variable, or if more than one independent variable is used to predict the value of a numerical independent variable, then such linear regression algorithm will change from what? Single independent, that is single or simple linear regression, to what? To multiple linear regression. Why? We are having more than 2 independent variables here. For the simple one, we are having only one independent variable. I hope you've gotten what? You've gotten that the difference. Okay? I hope you've gotten the difference. Are we together? Are we together up to that point? Good. Seems you are following, and please respond, like show me. It leaves me with doubt because I can only see thumbs for only a few people. It is my assumption that the others are also okay. Okay, yes, I don't want you maybe to that is uh, to search for me aside, maybe after class, for clarification, and you were I gave you the opportunity to do what? To ask or to comment during the class. So please, I'm also good. and sometimes I might also be tough. More so when maybe you are coming back with a question or with a concept we discussed. I usually welcome for all consultations, okay? Even work related consultation, no problem, okay? But now maybe consulting for a concept maybe which you did not understand and then you did not ask during the class, then you might wait maybe for a bit longer for me to respond. Okay. All right. So let's just be attentive and also ask questions. Okay. Now, when it comes to linear regression line, the linear regression line, we can have two types of linear regression line. It can be a positive regression, meaning an increase in y or an increase in independent variable, or an increase in independent variable triggers an increase in what? An increase in that is in our dependent variable. Like if the x variable is increasing, definitely the y value is what? Is increasing. That is for positive linear regression line. Okay. What about if the regression line is it's that is in it's negative? Okay. If the regression line is negative, meaning it's running from what? From maybe left to right. Okay. Okay. It is running, let's say yes, from left to, I don't know how I can explain that, but it's in this shape, meaning an increase in x value is triggering a decrease in what? In y value. An increase in x value is triggering a what? A decrease in what? In y value. For this case, we say this is what? It's a negative linear regression line. And for this one, if the value of x, as x increases, so does the y, then this becomes a positive regression line. Okay. All right. So a linear line showing the relationship between the dependent variable and independent variable is called regression line, which is this one. Okay. So we have two types of this relationship. Okay. That is positive linear regression, meaning if the dependent variable increases on the y-axis and independent variable increases on x-axis, then such a relationship is termed as what? Positive linear relationship. Why? As x is increasing, y is also increasing. All right. Then let's go to the negative linear relationship. So if the dependent variable decreases on the y-axis and the independent variable increases on the x-axis, then such a relationship is called negative relationship. That is, as x is increasing and y is decreasing, then this type of relationship is what? Becomes a negative linear relationship. I hope we are also good up to that point. That was simple. That was simple to explain. Yes, Kennedy?
Um, I just wanted to ask. My field my field is in research.
Mm-hmm.
So, in which circumstances can we apply the two types of linear regression lines that you are trying to describe? Though mine is more into health research, though. I don't know if that is okay for you to answer.
Okay. So we have an example. There is always an example which I got. In fact, health related example. health related example I want to give you, like an application. Okay, application of let's say positive linear regression. Just want to go, maybe just need for examples, that is real world examples. So like for example, let's take an example of medical research. Okay, we have this under medical research. Okay, so medical research often use linear regression to understand the relationship between what, the drug dosage and what, blood pressure of what, of patients. Okay, like here you are trying to check, maybe let me just go through these examples. Like for example, researcher might administer various dosage of a certain drug, okay, to patient, and observe how blood pressure responds. Okay, they might fit a simple linear regression to that data which they have they have collected. Like for example, you might have different dosage of a certain drug, like let's say even for blood pressure there is that that is pills, okay, which maybe someone gets to the hospital and his or her blood pressure is high. Okay, you usually give that pill to that patient and observe maybe for time interval maybe of 30 minutes. Okay, so after every 30 minutes, come we do what, we examine your blood pressure. If it was high, okay, maybe it might go down, or it might that is remain that is the same, what, the same, depending with what, with your observation. Okay, so now the researchers, they might fit a simple linear regression model using dosage as the predictor variable of blood pressure as the response variable. Okay, so the regression model will be of the same that is the same, what, the same or of the following form. Like for example, we are trying to predict the what, the blood pressure, the blood pressure value. Okay, yes, given a specific dosage, we have some constants here, okay, whereby the coefficient B naught and would be represented as the expected blood pressure when the dosage is what, is at zero. Okay, like for example, before you administer that is the dosage to that patient, you have the initial what, you have to get the initial, you have to get the initial um, reading of the blood pressure. Okay, then the first dosage after giving or administering the what, the first dosage, then the rate of the return, the rate of change. Okay, the rate of change now will be presented by what, by b2 or beta 2. Okay, so for coefficient B would represent the average change in blood pressure when the dosage is increased by maybe what, maybe 1 unit. Okay, so if B1 is a negative, it would mean that an increase in dosage is associated with a decrease in what, blood pressure. Okay, meaning as now we are trying to what, to control your blood pressure. Like as we are increasing the dosage, the blood pressure, it's what, it's reducing. Okay, so with that we can also collect a sample data and get to know which dosage or how many dosage do you have to administer a patient, for that patient's blood pressure to be at what? Normal range. Okay, so with that, you can always what? You can always measure those like those dosage up to the point where maybe the blood pressure will be what? Will be within the normal range. Like for example, also if B1 is close to zero, it would mean that an increase in dosage is associated with no change in what? In blood pressure. Like for example, if the constant or the second constant or the rate of change in dosage is very minimal, then it means there is that dosage which you are giving, it has no impact to the blood pressure of this person. It's neither that is reducing or going up. Like the rate of change is very minimal. Okay, but if B1 or the rate of change is positive, then it would mean that an increase in dosage is associated with an increase in blood pressure, and for that you would now not prefer to do what? To increase the dosage of this person. Why? Because as you increase the dosage, you can see the blood pressure is what? Is increasing. Okay, if maybe you are decreasing the dosage, okay, maybe the blood pressure is also what? Is also decreasing, then meaning that is with the constant, okay, or with the initial amount of dosage you gave that patient, it's better now to reduce if you are getting a negative value of the what? Of the in the rate of change. Then we also have other applications, like in agricultural scientists, they often use linear regression to measure effects of fertilizer and water on the what? On the water crops. That's another example. Also, data scientists for professional sports team use linear regression to measure the efficient that different training that is regimes, okay, have on a prayer that is or it is a determinant, like different trainings, okay, have that is has an impact on players performance. Okay, you can as well do such also such a research. Okay, so these are just examples. Okay, and you can get more examples that is online, more application, they are online. Okay, so you can go research more depending on your that is on your industry. You can go just how can I apply maybe linear regression in sports, how can I agree that is use or apply linear regression in agriculture, okay, or in agricultural data. Okay, yeah, so I guess that's okay. Kennedy, are we good?
Yes, 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 yes. That's helpful. Thank you.
Okay, that's nice. Okay, good. Now let's go to finding the best fit of a line. Okay, now we are trying to talk about now that is optimization. Okay, we are trying to discuss about optimization. How can we optimize our what? Our coefficients to get the line of best fit. And what does it mean by getting the line of best fit? Meaning we are minimizing our error terms. Okay, we are also minimizing our error terms. That is the distance between what? Between the data that is the regression line and the what? And the data points. Okay, the far the data points from the regression line, the large what? The large the difference, or the large the error term. Okay, and whenever the error term is high or the standard error is high, okay, that implies that we will have a very poor performing what? We'll have a very poor performing model. Okay, we'll have in fact less confidence in that model. Our model will be accuracy will be very low. Okay, our model won't be reliable. Okay, yes, now let's go to finding what? The line of best fit. And finding the line of the best fit, we usually use either cost function method or gradient descent. Okay, gradient descent method. Okay, right, let's try and check. So, when working with linear regression, what is our main goal? Our main goal is to find the best line. That means the error between predicted values and actual values should be what? Minimized. Very correct. Like we are trying to minimize these error terms, like the distance between what? That is the actual values and the predicted values. The predicted values, they are along what? They are along the line of best fit. Okay? They are along the line of best fit. Okay? Like maybe just to illustrate or just to give you an example. Okay? Let me just take these that is two these two variables. Okay, let me just take these two variables and I want maybe to insert that is a linear regression line. Okay, I just want to insert a linear regression line. So with that, I'm going to insert. Then I want what? I want a scatter plot. Okay, I want a scatter plot. Here it is. This is our scatter plot. Okay, so with our scatter plot, you can see how our data is what? How our data is distributed. Okay, you can see how our data points are distributed. Okay, then we might now decide to what? To add like a linear or the line of best fit. Okay, we want a linear line, or the line of best fit. Okay, let me just add that is the line of best fit. Don't worry, we shall cover practicals for this. Okay, we shall cover practicals for this, so don't worry. Okay, so you can see now this will be the line of best fit. This will be the line of best fit. And then the error term will be determined by the distance between what? Between also any value within what? Any value within the line of best fit is what? Is a predicted variable that is value. Also, you can always that is extrapolate, moving on and also going downwards. Okay, and see, like for example, if I increase the amount of rainfall or the amount of rainfall, if it increases up to 250 millimeters, what will be what? What will be the number of umbrella cells? In that you can be able to predict. Okay, so what I'm trying to mean is that that is the distance between or the distance of the data points to the line or to the regression line. Okay, the more it is that is minimal, or the more the distance is minimal, the more that is accurate. Okay, all the more reliable it's what? It's our model. Okay, but if the difference or the error term is high, then it means that is our line, it's not that it's we can't say that is we are having a line of best fit. Okay, we won't say we are having a line of best fit, otherwise we'll be able to do what, to do some adjustments on that. So our that is when working with linear regression, our main goal is to find the best fit line. So if the and how can we obtain this? It is by minimizing the what, the error term. Okay, so the best fit will have the least error, it will have the least error term. So maybe from this example you can see we don't have data points which are far away from the that is a regression line. So by the look of things, I can say that here we are going to get a good model. Okay, here we are going to get a good model, meaning our standard error will be what, will be very small. Okay, our standard error here will be very small. Okay, so take note of that. All right, good. Now, the different values for that is for weights, all the coefficients of the line, that is, let's say we are taking A0 and A1 to be our constants. They are our coefficients. Like it's like we are saying equal to that is y. That is y is equals to A1 multiplied by x plus A what? A0. This is our constant, this is our constant. Okay, so the different values of weights or the coefficient lines give different that is line of regression. So we need to calculate the value or to calculate the best values for A0 and A1 to find the best fit line. So to calculate this, we use what we call cost function. And what is cost function? That will be what? That will be our next topic. Okay, here it's the cost function. So what is this cost function, or what does cost function do? So what happens, the cost function tries to optimize the what, the coefficients, that is a0 and a1. We are trying to get the best values. Okay, and we usually say that the lower or the smaller the cost function, the better the coefficients. Okay, and the larger the cost function, okay, the less optimal our coefficient, meaning also our model would be what, would be that good. Okay, so the different values of weights or coefficients, okay, gives different linear regression, and the cost function is used to estimate the values of the what, of the coefficient of the best fit line. Cost function, okay, optimizes the regression coefficients or weights. As I have told you, it optimizes what, the coefficients. It measures how a linear model it's what, it's performing. So we can use cost function to find the accuracy of the mapping function, which maps the input variable to the output variable. This mapping function is also known as hypothesis function. Like you can hypothesize, that is hypothesize. Like maybe you assume this is the what? This is the best constants. These are the best constants to use in reference to what? To what you have. Okay. If your hypothesis is correct, then you will go with that. If your hypothesis it is wrong, then you'll have to go what? You'll have to go with that is with already available or calculated um, coefficients. Okay, and the cost function, we normally, now in statistics, we normally call it mean square error. Mean square error is the what? Is the cost function. So linear regression, we use mean square error cost function, which is the average of the squared errors occurred between the predicted values and the actual values. Okay, let's assume maybe we have what we have. Let's assume these are the actual values. Okay, y are the actual values. Okay, then y at is what? Is the predicted, that is values. These are what? These are the predicted, that is values. Let's assume here it is what? B, 1. So for us to get now the mean, that is the mean squared error, okay, we usually now calculate, that is the actual, that is the yi's minus y ats. Yi's, it is the actual, that is the actual value. Then y at is what? Is the predicted value. Meaning now, and for this, when we do the difference, we square. Okay, we usually square the difference. That is yi minus y at. Okay, actuals minus predicted, that is raised to 2, then divide by what? Divide by, that is n. Okay, we have divide by n, and this is the total observations. Okay, the total observations. Okay, so with this you can now as well say that y is minus the predicted, that is y at is equal to, that is 0 plus b multiply, or x multiplied by a what? A1. Okay, and this you shall square this. Okay, then divide by what? By n. And then we are doing summation of all this. Okay, we are doing summation of all this. Okay, that's how we calculate what? The mean squared error, which is the cost function. Okay, so if the cost function is small, it's a smaller value, then it means, what does it mean? We don't have a large, that is we don't have a large error terms. Okay, all the distance between the what, the actual values and the predicted values is very minimal. What am I trying to drive? Okay, like for example, if we have a regression line, okay, these are the data points. Okay, and then here we have maybe like the predicted that is values. For us to get a better, that is this, let's compare this. Here it's a, and also we have another one, b, with what? With error terms close to the what? To the regression, that is to the all the that is to the regression what? To the regression line. So of course this is b, meaning this will be more, that is at optimal, compared to what? Compared to this. In case we get this kind of model, what can we do to make it better? Is by optimization. Okay, meaning we are trying to do what? To minimize these errors. And one is called cost function, which that is aims at optimizing the coefficients for us to have what? For us to have a better, that is a model. So the above linear equation, it's all, we have, this is the calculated mean squared error. Okay, yes, then we have the residuals. Okay, the residuals is the, it's the what? It's the error term. all the vertical deviation. And I've said that residuals, they are distance between the actual values and the what predicted, predicted values. So if the observed values are far from the suggestion line, okay, then the residuals will be what will be high, like in the case of air, or air illustration air. Okay, and the cost function will be also I. Yes, why? Because the error term are what? The error term is also very high. So the cost function will be I. And the moment the cost function is I, then it means we have what? We have a problem in accuracy of that model. We won't get the correct what? Or a good accuracy of our models. Oh, that is of our model. But if the scatter points are close to the regression line, as in now example B, then the residuals will be small and hence the cost function will be small. So with this point we can say that is model B is at optimal or it is optimal or at optimum point compared to what? Compared to illustration A. Okay? Yes, that's all about cost function. Okay? Then I want us to finish with what? I want us to finish with the gradient descent. Now for the gradient descent basically works on the cost function. Remember we've said cost function you are working with what? You are working to that is to optimize the coefficients. Okay? Okay, to optimize the coefficients. Okay, this is the cost function. But now we have something else called gradient descent. Now gradient descent is used to make or to minimize the cost function. It is used to minimize the cost function, and in return we'll get an optimal value of what? Of our coefficients. Okay, then I will finish with the model performance. How do we measure that is goodness of fit? Or how do we measure the model performance? And this is by use of what? That is R squared. Okay? Yes, on gradient descent. So, gradient descent is used to minimize the mean squared error. Okay, gradient descent is used to minimize the mean squared error. And what is the mean squared error? We are talking about the cost function. Okay, by calculating the gradient of the cost function. That is by calculating the gradient of the cost function. So a regression model uses that is gradient descent to update the coefficients of the line by reducing what? By reducing the cost function. And this is done by random selection of values of your coefficients. Okay, like for example, if the value of our coefficient, let's say a that is was what was 0.9 and a1 was maybe at what at 2. Okay, or let me do the vice versa. This is what this is 0, this is 1. Yes, a1, meaning a1 is attached to the x variable. Okay, good. So if when using this if we are using this maybe coefficients, or if when using these coefficients we are getting a very small error term, okay, let's say of 2.3. Okay, now we can randomly select the values of what? Of a1 and that is a0. Like for example, we can check when maybe we are increasing the value of what? the value of A1, what is happening to the error term. If the error term is increasing, then we'll have to reduce what? Reduce this. And now reduce it up to the what? To the smallest value. Okay? To the smallest value, even if it's 0.5. Okay? If the last value we can get is 0.5, okay, then that will be what? Will be the optimal value to use, okay, as our constant. Okay? That's why we are saying that for gradient descent is done by randomly selecting the values of coefficients and then iteratively updating the values to the what? To the to reach the minimum cost function. Okay? Then updating it to reach the maximum cost function. Then with that, we'll be able to what? To also optimize our model. Okay? Then the last slide, so that maybe I might take questions or suggestions or additions, is that model performance. How do we measure model performance? So we have the goodness of it determines how the line regression or the line of regression fits the set of observations. Okay, the process of finding the best model out of various models is called optimization, and this is achieved by what? By calculating what we call r squared. Okay, r squared. If we get the value of r squared, okay, close to 1, then we'll say we'll have what? A very good that is model, or the model we can now say this model is a good fit for our data. Okay. Yes, and r squared is also known as coefficient of determination for simple linear regression and coefficient of multiple determination under what? Under multiple linear regression. Okay, so r squared is a statistical method that determines the goodness of fit. Okay, it measures the strength of the relationship between the dependent and independent variable. Okay, we shall come to something we call multiple R. Okay, multiple R, that is R. Here it will be basically the correlation. Okay, the correlation of the two variables. Okay, and it measures them in a scale of 0 to 100 or from 0 to 1. The higher the value of r squares determines the less difference between the predicted and the actual values, meaning it will mean that we have very small error term. Okay, hence this will represent what? A good model. It is called a coefficient of determination or coefficient of multiple determination for multiple regression. And now I will share the formula maybe tomorrow, and also I will explain it when we will be doing what? When we will be doing that is the linear regression. So for linear regression, we'll use three approaches. That is using the linear graph, okay, or the linear line graph. We'll also use analysis tool pack, and we'll also use inbuilt Excel functions. Okay, to calculate what? To calculate those coordinates for us to or those values for us um, to get the that is the model. Okay, so tomorrow we will start on the assumptions. Okay, tomorrow we'll start on the assumptions. Then after the assumptions, we'll now go to what? Preparing the data. Okay. After preparing the data for analysis, okay, we'll do what? We'll now do the practical for what? we'll now do the practical for linear regression and then check on interpretations. What interpretation when it comes to that is to checking if our data is significant, if our model is reliable. Okay, yes, that's all for today's class. I now welcome that is I now welcome oh, you mean I did not that is record that, but no worry, I still have the last class that is recording, so I will still share the same. So any question up to that point? Any question up to that point? Can you please use real values to show how we get the cost function? That we'll do during the practicals. So no worries. Should we expect any data set for? Yes, we shall still work with the. Maybe we shall still work with the umbrella cells, or maybe you can come up with maybe your data set, provided it has what? It has a relationship. Okay, that is a relationship. We have a linear relationship between what? Two variables. Okay, all right. Yes, Naomi.
Just,
Naomi.
if you don't mind, yeah,
Mm-hmm.
just a second. Sorry, I was just getting off one class. If you don't mind, if you can use the same data set, maybe you tell us in advance so that we can follow through the class. Assuming some of us we've never done analytics before, so I'm just suggesting we don't all come up with our own data set. It will inconvenience the class tomorrow.
Okay, so I will share the data set. We'll still get that is what do do like I'll share the umbrella cells data. No problem.
Okay, thank you.
Yes. Can we get these slides? Of course, I will share the slides. I will share the slides. Huh? Another question? Any other question? Okay, if no question, I guess we are all good. I guess we are all good. And I hope, how was the class? How was the class? Did you understand? Did you get the concept? How was the class? Did you get the concept? Okay, Aini, all good, makes sense. Kaka, yes?
Hello, good evening. Okay, so I believe that it's a good time for us to work on ourselves. So far, the last two topics have been a little bit, I can say, complex, a little bit complex. So I think we need to have our own follow-ups and our own research on the uh, linear regression and so on, cost function. Yeah, the last subtopic I did, I can say some things did miss me out, but I'll try to uh, catch up with them later on with my own research. So I believe everything is well, but yeah, it's a high time that we work on ourselves. Maybe you can appreciate even some more assignments and so on.
Okay, okay, no problem. If you want assignments, I have assignments which I can give you. So, yes. as I had said from the beginning, now things are now becoming complex as we do what? As we move on. So make sure you do what? We get those steps. Okay? We get those steps. All right. So with that, I can see maybe Dennis, today you were quite fast towards the end of the class. You did not say that. You did not maybe uh, tell me you are fast. Up some concepts. Yes, I will still do a recap when we'll be doing practicals. I hope you will understand or get. Um, Kennedy, it is getting interesting each and every day, quite enlightening. That's okay, meaning you are good, you are following. Michael Mulamba, you were fast towards the end, you did not say as well, and this is the problem which I am trying to avoid. Okay, because if you had maybe told me, please, you are too fast on this, you could have raised the same. All right, because I always try to avoid that is the problem of repeating myself. Okay, please always communicate. I've given you freedom. I'm not that is harsh on you. Okay, so please, if maybe I'm fast at any point, always reach out or always unmute and tell me, sir, that concept I did not get it clear. Okay, then a few new concepts introduced. Looking forwards to the practicals for better understanding. That's okay. We can reconsider even group work so we can relate. Okay, that's all right. I will share some. That is, I will share some assignments on Thursday, so that maybe on Friday and over the weekend you can do what? You can work on them and then have a discussion later on. Okay. Then we have Michael noted these things and sorry. Yes, please always interrupt. Okay, it is better to interrupt than for myself to come. Of course, I will love to be interrupted than maybe to be taught in a next class. We did not understand this concept. Please repeat. Okay, I would love to be interrupted for me to explain. Then sometimes we should be assigned some work. Yes, I will give you assignment because of course we can't finish that is the class without assignments. I will give you assignments, and my assignments are always tricky. Okay, it needs that is brainstorming. Okay, it needs brainstorming, and I will share that. I will share that is on Thursday. Yes, Kaka?
Okay, maybe backing up on what Kennedy said, perhaps maybe we can have more group works. I believe on Friday maybe can work for us, maybe student only, maybe for us. I think some of us get more knowledge while we are engaging ourselves, maybe in discussion, can ask discussion and the sort. Maybe we can arrange within our own selves. Maybe we
Yes,
create maybe one group on Friday.
yes, I don't have problem with that. You can always regroup, discuss, and areas where you identify some gaps or you have questions to ask, you can now come to me. Okay, you can now come to me and tell me, oh, sir, we had a discussion, we came across this topic, we did not get it clear. Okay, what does this mean? Then I will be able maybe to do what? We will be able to discuss together. Okay, we'll be able to discuss together and come up with a solution. No problem. You can always regroup uh, and discuss. Choose a topic and discuss. Okay, okay, Kaka.
Okay, that's well noted. I'll be the ringleader to that.
Okay, no problem. Yeah, so you can always do your discussion. So I will be now, you will be now maybe asking questions to the topics which you did not understand, maybe on the next class. Good. Otherwise, that's all good. At least I got this today. Now I can say things zimechemka, things are becoming are boiling. Aini, maybe you might miss that. Vitu zimechemka, like things are now have started boiling. Okay, yeah. So yeah, that's now the statistics. That's now the statistics. Now, and we are moving to complex part. When we'll be discussing about distributions, it will be crazy. I know, but I know most of us usually that is go through and also pass through exams. The good thing is under distributions they usually don't ask that is set practicals under distribution because they know it's a very complex topic and like if you are given one question under distribution, it can take you even 40 minutes. Okay, so the good thing under distribution, they usually test your knowledge to the properties or understanding that distribution. Like for example, maybe you might be asked, is it true maybe in normal distribution is the mean equal to mod equal to median? Okay, so what are the properties of normal distribution? So that is mostly what is tested, more so the properties of distributions, because for the practicals it's crazy. It's crazy. All right, so thank you for your for joining on today's class. I am hoping tomorrow to have a more interactive class. Okay. Otherwise, have yourself a great night. We'll talk. Good night and bye bye. And remember, I had already said that um, we usually say, okay, standard error, it's kind of deviation